Before I start this afternoon, recall that who want to participate in the dinner tomorrow, please contact Leticia, and who wants to participate in EDAÍ this Friday, please contact to Lorenzo for inscription, for registration. So it's a pleasure to me introduce the first speaker this afternoon, Ali Tahzibi from USP San Carlos, who talk about some roles of the unstable entropy.
Okay, good afternoon. Thank you very much for introduction. Thank you very much for the invitation. I'm really honored to be here, my first home in Brazil. Of course, it will not be very easy to talk about Jacob, about the experiences, but at the end, we should talk something besides mathematics. So I begin with my chances. So one picture is Shashahani, who was colleague of Jacob Palis. So Shashahani was my mentor at undergraduate at Sharif University in Iran. And like others, almost all of the students went out of the country. And I was really lucky that I arrived here and continue with the same school, the Berkeley School. Both of them were the student of Steve Smale. And well, I arrived here really lucky and almost like familiar. Well, maybe just the second slide is about a quote that we heard about Jacob and some of his methods to encourage people. You will see in the second slide of my talk. I was just verifying with some of my colleagues. One of them is Chicago University, another one in Iran at the right moment. He was a student of IMPA also, and also a colleague at IMPA. All of them said me that you should be very courageous to say about this slide, but I am really confident enough that you will understand, and certainly Jacob will understand, that why I am putting this slide here. So you will see all of us talk that Jacob is kind of a religion. Jacob is kind of a different kind of encouragement statement for us. And you can see how he can manage to say to other country people something even about Brazil. You see, so some people say to me that they will kick you out. I hope that it will not happen, so I'm confident. So Shashahani said that when I began to talk with him, with Jacob, about the difficulties and beginning of the PhD in Iran, he encouraged me too much and was very optimistic. He said, know that Brazilian PhD program is well established and produced excellent results. I can reveal you a secret. Jacob said, do you remember that math master dissertation that I gave you in Brazil? And Siavash Shashahani said, yes, but the dissertations here in Iran are much higher level than that. And Jacob said, it was a PhD thesis. That time I didn't say you. Your V0 is very high, so go ahead. Okay. Well, I don't hope that everybody will like, even my colleagues, because the PhDs begin here like any other countries, slowly, of course. But it is very courageous act of somebody saying to other countries' people that you are very better than us now at the beginning, but of course they are excellent. He said that Brazilian program is well established and they're excellent, but he was kind of encouraging them to begin their PhD because you are even better than us. It is just marvelous way of doing this. I think that almost nobody that I know can do like him, to do this with his generosity and it is greatness. Okay, I have one picture. I just asked my wife today to send me. This is picture with Jacob in 99. I arrived here in 98. It is almost 22 years. I arrived in March 1998. And the picture is also very important to see somebody is dancing. So this is a barbecue at IMPA. We had barbecues at IMPA, and people speaking, talking, dancing, and Jacob was with us, speaking, dancing, drinking, etc. Very well. I hope that I will not be very late, but as I said you, in my modest opinion, I consider the way that he acts is a kind of religion. So it has commandments. I put the commandments in my testimony in the book. Of course, not all of them, but other students can help, like comer pela beirada or go deep, and many others that I wrote some of them, and there are some commandments. I would like to highlight his intrinsic generosity. So by intrinsic generosity, I mean some character of a person, when he does his generosity, you don't even believe, you don't even see that he is acting, he is not pretending, he is doing it very naturally. So the deepness and excellency is very important. It is an example for many other countries. If you want to begin some postgraduate, some doctoral, some school, you should really go deep. And this is one of his commandments that even recent years he saw me and said, continue with good mathematics and deep mathematics. The students know, you should continue with good mathematics and deep mathematics. It is very important. Almost everybody knows that IMPA began almost a very fashionable dynamical system. And the way that the IMPA progressed was kind of dynamics, which is dynamic of IMPA. So this has some controversial statements, because you don't touch, for instance, Margulis type, homogeneous dynamic type, or other type of dynamics. But what you are doing one deep, excellent dynamics, and you're growing up to the top. So you create fields medalists even. So this is, I think I can understand that this was the idea of Jacob. And all of us, like other students, I was lucky. I was at the same time that Artur and Jairo Bocchi, Federico Hertz. There were many, many good mathematicians there at my time here, like even though, of course. And you know these guys that I said. And we were always inhaling and exhaling this kind of homoclinic tangency, fractal dimension, etc. And of course, that your academic legacy will be for us forever, and your behavior to study mathematics and to treat people, of course, will pass through the students, which will be vectors to the other people. So thank you very much for being you. Okay, let me begin now my talk about something that doesn't have anything to do in principle with Jacob's conjecture, but during the talk maybe I didn't have time to relate everything to others, but you will see that there are many moments that we think on some proposition, on some theorem, but it is important how we think. And people like Jacob form your way of thinking. I think Artur was saying something like this in the morning, that the way that you think mathematics is influenced by your mentors. So what Jacob did, I think the most important thing is that you want to think in this way. Okay, so let me go ahead and maybe show you some examples if we have time. The entropy theory is a very nice history. So it is a matter of a statistical mechanics and information theory. So the two big names we can highlight, Gibbs and Shannon. And of course, this notion came into dynamical systems in the way that we work in ergodic theory by Kolmogorov and his students Sinai and the people around, of course. But the main authors to well, of course, Bowen, but the main person who introduced entropy was into the dynamical system Kolmogorov and Sinai, who effectively calculated also some entropies of dynamics. And well, almost everybody should know about the definition of entropy, but let's be patient and see the definitions also. So I hoped that my transparency is larger. This one was one of the commandment of Jacob to have the letters very big enough. I never forget, but sorry again, I didn't succeed that. So you have a measure preserving transformation. You have a partition in your space into measurable subset. So you take the average of the information, you have this entropy, and you act your dynamics, and you want to calculate how your dynamics generates entropy asymptotically. So after n iteration, you calculate how much you created information, and then you substitute from the previous time, and this limit is called the entropy in dynamical systems. So it is, if you go to the history of these things, you see that it began from something from statistical mechanics, and then it go to number theory, analytical number theory, etc. So it is really kind of fantastic thing in mathematics. So you consider, okay, related to the title of my talk, I will fix, in fact, some expanding invariant foliation. So you have a dynamical system, which is C1 dynamical system, and you have a foliation, okay, a foliation F, which is invariant by your dynamics, and it is expanding, okay, uniformly expanding. So how to define the notion of entropy along defoliation, this foliation? So let me just say that, going back again to Sinai, so when he was calculating entropy, he just knew that the entropy should be hidden in the unstable direction of the dynamical system, in the direction where you have kind of expanding. So if you have some expanding foliation, it is natural to expect to define the entropy. So you have two kinds of entropy. One of them is topological entropy. By topological entropy, you want to calculate how the points will be distant apart after iteration by the dynamics. How is the growth, the growth rate, the rate of the growth of this number of the points that are spanning some region, some local ball, some ball. So you define n epsilon a spanning set. Okay, this is again the initial definitions of entropy, and then you define the entropy of the unstable foliation. Of the foliation, I put here unstable because that expanding foliation typically will be some unstable foliation. Okay, and you do the usual calculation, and you define the entropy as these growths. Okay, so it is well worth to say that topological entropy along expanding foliation is nothing more than the volume growths along the foliation. So you have some ball, and you calculate the volume, the Riemannian volume along on the foliation, on your expanding foliation, and then you iterate and calculate how it increases, and the rate will be equal to the topological. So this is a very good notion to define, easy. And then you want to define metric. So you want to define complexity in terms of some invariant measure of your dynamical system. It turns out that it can be defined in some cases easily, but in general, when you have some expanding foliation, you don't have necessarily a very canonical, simple way to define this. So to define the metric entropy in this general setting that I posed for some expanding foliation, then you can define the entropy beginning with a partition again. So you should have a partition which is called subordinated to this foliation. So every element of partition is a subset of the leaves of the foliation, and you want, well, that the partition is kind of Markov partition, so you expect to have a kind of Markov partition, and the elements of partition are not trivial, so they contain some open set. So if you can construct such a partition, then you define the entropy equal exactly as the conditional entropy of the f-1 condition to your partition. So observe that f-1 of psi is a partition which is larger than this partition, or more finer than the partition psi. So this number can be positive, in fact. Indeed, it is positive in the unstable case for typical some good measures. Very good. So it is interesting also to mention that there is a variational principle also by Hua and Hu. They prove that really the topological entropy along unstable foliation is exactly supremum of the entropy with respect to invariant measures. Okay, so my aim in this talk is to outline at least 2 or 3 application of using this entropy along the foliation, along the unstable foliation, and pose some questions and projects if you desire to. So, okay, so this entropy, well, Zhegang Yang had a paper where he constructed this kind of partitions for every expanding foliation. So, and he shows that, well, this part is not his main contribution, the upper semi-continuity of this function. So whenever you have an expanding foliation, then the entropy function is an upper semi-continuous function. So this means that by using abstract analysis, you always have a measure which maximizes the entropy. Okay, so every semi-continuous function admits its extreme points in some compact domain, which is the set of invariant measures. So you have some, so for any dynamical system, any C1 dynamical system, if you have some invariant expanding foliation, then you will have some measure which maximizes. So remember that for dynamical systems, you may have dynamics where they don't admit measures which maximizes the entropy, the genuine entropy, which is called metric entropy. But here we are talking about the entropy along the unstable foliation. Okay? So one of the projects is to understand the structure of measures of U maximal entropy. So I would like to understand how are these measures in the non-uniformly hyperbolic setting, in partially hyperbolic setting, etc., etc., etc. Okay? So let me go a bit into details. So for the first example, I need to recall a definition. Maybe this definition is not familiar with all of you but, who had done dynamical system, I mean the students. But it should be. So Margulis measures, if you have an invariant foliation, so you take an invariant foliation, now this definition doesn't depend on expanding or not. So you take any invariant foliation, so you say that a family of measures are Margulis family of measures if first, for every x on the manifold, the measure depends just on the leaf. So the measures are defined on the leaves of the foliation. They are Radon measure. They are non-trivial measure. Okay, they are locally finite Radon measures, and they depend just on the leaf. Okay. they satisfy this continuity property. So when you fix a foliated box, then your measure from here to here varies continuously. This can be written precisely by taking integral over continuous functions, continuity of some integral, of course. And importantly, the most important property maybe is that your dynamical system acts as to be linear with respect to the eyes of this measure. So with the viewpoint of your measure on the leaves, your dynamics is acting linearly. So this is f star of mx is equal to d times m of fx. So for instance, for example, if you consider some linear automorphism of torus, 2, 1, 1, 1, this favorite example on T2, to T2, then you have a foliation expanding eigenvectors, eigendirections, and then the Lebesgue measure along these leaves, of course, will be a Margulis family because they vary continuously. It is always the Lebesgue measure for every leaf. It is not finite measure, of course. It is sigma finite measure. And if you iterate Lebesgue here, f star of mx, you go to another leaf, f of x, and it expands. Or in the contracting direction, it contracts. Okay? So no, this example is not too far from our very old friends, which are the maximizing measure for uniformly hyperbolic dynamical systems. So if you consider, for instance, some transitive Anosov diffeomorphism, or even for the basic sets, you can do, you should do the same. I will restrict myself for the Anosov because we can do it really for the foliation, not necessarily for the moment for the lamination geometrically. So what happens is that if you have some uniformly hyperbolic dynamical system, then you have two transverse foliation, and there are two family of Margulis measures. Okay, and the product of these two measures, of course, it should be defined locally. The product measure is the measure of maximal entropy. So the measure of maximal entropy is exactly locally for hyperbolic sets, for uniformly hyperbolic sets, is the measure who sees your dynamics as to be linear, as being linear. Okay, of course, you can imagine that the d, this d. This affine constant, this dilation constant, is exactly the exponential of the topological entropy. Of course, the mu s, which is defined on the stable foliation, will be inverse. The constant will be inverse of d, and then this will give you your invariant measure. So what I would like to emphasize is that maybe I myself, I should say about myself, I knew about the Bowen approach, which is via periodic points and the specification. And there is also another approach, which I'm trying with my colleagues to push for some partially hyperbolic dynamics, which you do not necessarily know about their specification property and this kind of things. Okay? So, and here is what appears unstable entropy issue. So holonomy invariance is another thing that you have by the construction of these measures. And indeed, this holonomy invariance will imply that these measures vary continuously. So the measures mu u leaves on the unstable leaves, so you have two unstable leaves, and the measure from here to there is the same if you apply the holonomy by the transverse foliation. So you have two leaves of unstable, and you go through the stable holonomy, and the measure here is pushed forward to measure over there. So this, as holonomy varies continuously, you essentially conclude also that these measures vary continuously. So it is kind of, I would like to emphasize that it is kind of surprising, and it is kind of rigid property, because to have these measures are kind of conditional measures of your measure of maximal entropy, and conditional measures are typically this kind of almost everywhere. So everything is almost everywhere. In measure theory, everything is almost everywhere. But it is interesting for this measure in this uniformly hyperbolic setting, you have everywhere. It is kind of thing that I at least ignored for many times, that about this striking fact that it is defined everywhere, the conditional measure. Okay, so jointly with my colleagues, Jerome Bouzia, or Say, and Todd Fisher in the US, we worked for generic transitive diffeomorphisms close to time one map of Anosov flows. So this is a category of partially hyperbolic diffeomorphisms which are isotopic to identity. So it is interesting to mention, now I open, maybe later I will open this parenthesis. So this is an advertisement to say that we had a preprint. I will not go into the detail of this result, but we worked using this Margulis idea, pushing these ideas through the partial hyperbolic diffeomorphisms, which are close to flow. In fact, they need to be flow type. It means that the center foliation is fixed. And then we managed to construct these Margulis measures, and we found some dichotomy about the measures of maximal entropy. Okay? Well, this work is going to be continued and developed further, joining with Mauricio Poletti and Sylvain Crovissier, and also Jérôme. So we are improving much beyond also. So let me just now go to this parenthesis. I really believe strongly that these kind of things are real. So you work on something, but you always have in your mind the thing, or you are influenced, of course, by these waves of the other mathematicians. So you have lack of hyperbolicity, then you go through heterodimensional cycles or tangencies. Okay? This was inhaling and exhaling always at IMPA. And then you had blenders. So I don't see blenders, I cannot separate blenders from this history, of course. It is related to, if I am not wrong, the first by Lorenzo Gias at his thesis to go and establish this bifurcation after the heterodimensional cycle. So it is always related to this bifurcation. And it is very, very amazing that for the first time, I'm very proud that with my colleagues, Federico and Hanna and Raul, we used these issues where here we're coming from lack of hyperbolicity to prove the PUC-RJ conjecture in the two-dimensional center dimensions, using it, in fact. I'm not saying that it is the proof, of course, but it is important to say that, okay, if the blenders did not exist, this proof also did not exist, certainly, and I adopt that other proofs that came after our results, generalizing to high generality by Sylvain Crovissier, Amy Wilkinson, and Arthur, also would not exist, probably. Okay, so, well, for our mathematicians, these kind of arguments are trivial, but sometimes we should stress them, about them. So blenders goes to the minimality of foliations, so there are many, many things here, and then you have tangencies, and tangency are related to entropy conjecture. So away from tangency in C1, you have entropy conjecture of Mike Schub. There are results by Marcelo Viana and Shaw, if I'm not pronouncing wrong his name, I hope. Liao and I don't remember the third name, unfortunately. But there are many results. There are results by Pujals and Sambarino about the set of diffeomorphisms which are local constancy points of entropy. Anyway, I would like to emphasize that these results may not exist if you don't have this stress of these things. Okay, so let me come back to the Margulis construction. No, not Margulis construction, but the proposition that I consider as very crucial. So I hope that you at least will go outside of this room and remember that if you didn't know, that the Margulis family of measures is a family of measures which varies continuously, defined on the leaves, and the dynamic acts linearly. And this is the magic property. If you have a dynamical system, okay, so suppose that it is partially hyperbolic, admitting, so partially hyperbolic, here everybody inhale and exhale probably, partially hyperbolic, you have a stable, unstable, and centered bundle, you have the unstable foliation, and suppose that your unstable foliation has some Margulis system, mu, with multiplier du, then what happens is that this unstable entropy is always less than this number. So this is a nice beginning, of course, and it is not completely trivial. It is something which is base for many things. In fact, I will show you. Well, the equality occurs if and only if the conditional measures of your measure mu are given by the Margulis family. So this means that in the equality case, you have really very rigid case. And the argument, well, this guy, François Ledrapier, is also one of the people who you listen few when you talk, but he has many results. Almost all of the results that I worked in ergodic theory comes from François Ledrapier's results. So his convexity arguments, which is essentially we have rewritten, in fact, in our paper with Jérôme Bouzy and Todd Fisher as a part of the proof, of course. But this is, I would like to emphasize that this will be a key property. Okay? So the proposition, this proposition says that if you have a Margulis family with dilation, then exactly the topological entropy is equal to the constant, this dilation constant of the Margulis family. So the problem, of course, is the existence of this Margulis family. The construction is not trivial. It's not easy. I will not go through never today in this construction, of course. It needs some time. But I can put some question here that is following. As I said you, that there always exists U measure of maximal entropy. For every C1 partially hyperbolic dynamical system, there always exists an invariant measure which maximizes entropy along the unstable foliation. So the question is, well, very naive question, is that are they always Margulis measures? Are they always, is it true that you should be acting linearly? Well, it seems very naive question, and it is, but I don't have any answer. I'm not sure that it is too easy, in fact. So let me go to show you another example of the application of this kind of unstable entropy, which is related exactly to that proposition that I put, which uses convexity argument, which is this stuffs of rigidity, measure rigidity, which began by Katok and his schools, etc. Katok and Spazier, for instance, has a very first paper when they, in particular, for instance, show that if you have these two hyperbolic matrices, they are independent, these two matrices, but they commute, so they generate an action of Z2, in fact, okay, on 3 torus. Then they can prove that some kind of Rudolph statement for rigidity. So you remember the Furstenberg conjecture. There is a well-celebrated 2x, 3x conjecture of Furstenberg, which asks for the invariant measures, which are invariant by both of these two guys, ergodic invariant measures. So the conjecture of Furstenberg is that either the measures are singular and on periodic points, finite sets, or just the Lebesgue measure. And, well, it is not proved yet, but Rudolph had proved it very nicely. If the entropy of measure for one of these two dynamics is positive, then the conjecture of Furstenberg is correct. Well, of course, if the entropy is positive, then the measure is Lebesgue. It cannot be finite. And what Katok or Katok's school, they decided to work was that go beyond this one-dimensional thing and go to the actions. And then they proved that, similar to Rudolph, and I would like just in one transparency emphasize that one of the main things in the proof is also that argument of convexity, in fact. So the Lebesgue measure in this case is Margulis measure for the, well, you should define the foliation here. I will not enter for the foliation for the actions, but you can agree that there is some Lebesgue measure here, and the foliations are linear foliations, and the Lebesgue measure is exactly the measure which is Margulis family. And then they verify the entropy formula for any measure which is invariant and has positive entropy. They can show that this is kind of Pessin formula. They prove some kind of Pessin formula for some element of the action. And if you have Pessin formula, it means that you have the entropy is equal to the logarithm, the integral logarithm of the number. So then they use exactly that proposition, which is the core part, that if you have entropy is equal to the logarithm of some constant, then you know which this constant comes from the Margulis family, then exactly you conclude that your measure should be exactly the Margulis family, which is Lebesgue in this case. Okay, so this is one of the, okay, I would like to advertise a publication of SBM, Brazilian Mathematical Society, Contemporary. There is a volume which is written by Aaron Brown, and there are many appendices by Dynamical Arioka's people, and it is a very fantastic volume of this publication of SBM. I really suggest people in a smooth ergodic theory to learn. Aaron Brown had written a very nicely the proof, and the appendices are also written very well. I received this from SPM. Okay, so we are, who is my, Carlos, how much time I have? I began a bit, 10? Mm-hmm. So I know that it is a bit really very ambitious talk. In fact, this talk, I'm using it to finish the survey that I promised to nonlinearity to finish, and I am doing the advertisement. But of course, a survey cannot be a talk. But anyway, I'm trying to do the things for the same goal. So the invariance principle is again something which is related to unstable entropy, and I'm really happy to say that the relation between this invariance principle and the unstable entropy was a bit hidden. It existed. You see, this issue, invariance principle, is very old problem, and I think that with Jiagang Yang, we had the first time where we shed light to this invariance principle using really the entropy which was hidden, in fact. Okay, so maybe I forgot names, but of course the culminating part of this invariance principle is by works of Avila Viana and Avila Viana, Wilkinson, and Santa Maria also. Okay. But again, this began with Francois. So okay, I have just some minutes to state the theorem for you, and maybe convinced that we are using again unstable entropy. So it is a bit general setting. You have some probability space, you have some cocycle. For people who are adapted with these new cocycles, continuity of Lyapunov exponent, these days of IMPA, all of the people know. But okay, in general, you have a probability metric space, you have a cocycle over this metric space, and then I have here the picture. Picture is better. Maybe you have here, for instance, the shift space, and then you have some fiber bundle. Consider just trivial fiber bundle, okay? And then you have a partition here on your basis space. This is sigma u. Sigma u is, for instance, you can consider the unstable partition of your shift or anosoph diffeomorphism, okay? And now you can push to the upstairs. You have these center unstable partitions, which are just pre-image of this partition, okay? And then you have a finer partition inside again, which is the strong unstable partition, if you want. So you can, for people who understand well partial hyperbolic dynamics, you have a partial hyperbolic dynamics. Here you have the quotient dynamics, which is an anosoph homeomorphism. So of course it is not case of all partial hyperbolic. I will announce for you what is the setting. In the general setting, I'm just assuming that M is probability space and N is a compact space. Compact, in fact, I did a compact manifold. So I just say to you what is sigma u, what is these partitions, and then our result is the following. Jointly with Jagang Yang, we proved that the entropy of the unstable foliation, here is the entropy of unstable foliation, is always less than or equal to the entropy of the downstairs, okay? And the equality happens if and only if your measure on the unstable, a strong unstable leaves, all of them project to the same measure. This is the same as saying that the central measure, these are the center leaves. The central measures are invariant by the unstable holonomy. Okay. Sylvain and Mauricio Poletti, Sylvain Courvoisier, they highly generalized these kind of things to the non-compact fibers. Of course, they have some technical conditions, but their results imply our result as a corollary also. So let me go through the application. So the application is for partially hyperbolic dynamics, as you can imagine again. So I have a dynamically coherent partially hyperbolic dynamic with compact center leaves, okay? And the quotient dynamic is transitive anosoph, and the dynamic can be seen as a smooth cocycle over the quotient dynamic. We assume that there exists some holonomy between center leaves, okay? And the invariance principle that we proved is that if you have some partial hyperbolic dynamics satisfying these properties, mu invariant by F, then the entropy always is less than the entropy of the dynamical system, partial hyperbolic dynamical system with respect to the unstable foliation is always less than the downstairs entropy. So if you want to remember something strange from this theorem, you remember that the entropy upstairs is less than the entropy downstairs. Of course, it is not correct if you formulate wrongly or correctly. So here it is the unstable foliation entropy. So the unstable foliation entropy is always less than the entropy downstairs, and equality holds if and only if you have this invariance principle. This is called the invariance principle. And to finalize, essentially, this as a corollary, it says that if all central Lyapunov exponents are non-positive, then the same setting, partial hyperbolic, compact center leaves, etc. And if all central Lyapunov exponents are non-positive, then your invariant measure should be U invariant. Its conditional measure along center is invariant by the unstable holonomy. Okay. Maybe 1 or 2 minutes, just 2 minutes. In 2 minutes, I give you another application, which is, in a joint work with Raul and Federico and Hanna, Hertz, Ures, we proved that in this case, partially hyperbolic dynamics with one-dimensional compact center in three-dimensional manifolds, you have a dichotomy for the measure of maximal entropy. Either you have 0 exponent or you have some measures with positive exponent and some measures with negative exponent. And what I would like to emphasize is that we jointly with, okay, this is the first case when you have 0 exponent, okay, and here you have more than one measure of maximal entropy with non-zero exponent. So generically, measure of maximal entropy are hyperbolic. And jointly with Jiagang Yang, we prove that even high entropy measures are hyperbolic. So in this case, all of the ergodic measures which are maximizing entropy are hyperbolic, but using unstable entropy, essentially, really, we prove that even measures with high enough entropy are hyperbolic too. So this was not to say nothing about that, but what I would like to put the question, in fact, to put a new example also here, is that, again, using these entropies, unstable entropies, I'm able to construct measures which are maximal entropy but are not maximal entropy for unstable foliation. So if you have a measure which maximizing entropy on the unstable direction, it is not reasonable to hope that it is maximizing the entropy for the dynamics. But if it maximizing entropy for the dynamics, maybe you can expect that in some cases it maximizes entropy on the unstable. Of course, if you don't have center, then you are always maximize unstable. But what happens is that you can construct measures such that they are maximal entropy, they have positive central Lyapunov exponent, and using these invariant principles and the criterion that I put for you, well, of course, this is going to be recorded so you can see after. The entropy of these measures, which are maximizing entropy, is less than the topological entropy along the unstable foliation. So these measures, which were measures of maximal entropy, are not definitely measures which maximizes unstable entropy. So my question is, firstly, the second question, understand dynamically, what does it mean? What is this supremum over all of the entropy, unstable entropies of measures which are maximizing the genuine entropy? Okay, so this I don't know in general how to what to name it. What is this? And also there is a question which is related to our result with Jiagang about high entropy measures. So this diagram is coming from Lorenzo, Catherine, and Ram's paper. So they also had this kind of results of high entropy measures are hyperbolic, but in another setting, which is iterated function systems. So in the partial hyperbolic setting also we have this diagram. So here is central Lyapunov exponent, and here is the entropy, and there is here a gap. This gap is not known for me in partial hyperbolic setting. What does it mean? So these two numbers are numbers that I would like to understand. Maybe physicians know the answer. Sometimes I verified before Le Drapier and Young, there were many physics people like Procaccia, Grasberg, etc., that they had all of these Le Drapier-Young issues in 2 pages or 3 pages. But okay, no proof were available. I finish my talk. To put it, this was in the talk of Davidovich yesterday, which again says about the way that Jacob thinks and the modest way, and the very firm way. In the same moment, he is modest and flexible and firm at the same time. This is the religion that I talked about. Okay, so he's not unfortunately here, but happy birthday to Jacob, and thank you very much.
Okay, question or comment for? Well, if not, we thanks again, Ali.
Thank you.